Hi, everyone. I'm giving the first lecture in the course on zero-knowledge proofs, and my lecture will be an introduction to zero-knowledge interactive proof. And I'm very happy to be co-lecturing with Dan Bonnet, Don Song, Justin Thaler, and Yupeng Zhang. So we're talking about proofs. Let's start with classical proofs. So when we think of a classical proof, we think about these very esteemed provers, Gauss, Euclid, Emil Noether, Alan Turing, and our own Steve Cook. And we think about theorems, the kind of theorems that you learn perhaps in geometry in class, where there's a bunch of axioms, there's a claim that you're trying to prove, or a theorem. You make a sequence of derivations from the axioms, and then eventually you declare the theorem is proved. It could be the prime number theorem, the Pythagorean theorem, and so forth. But today we're going to think of proof as an interactive process, where there is the prover, but maybe more importantly for our study, there is a verifier. So there is an explicit reference to whoever it is that's reading the proof and verifying it is correct. And we think about this as follows. There's a claim, which is an input to both prover and a verifier. Both of the prover and the verifier are actually algorithms. And the prover sends a string, which we will refer to in this slide as the proof. The verifier reads this. So if you would like to think about that geometric proof, the verifier is the teacher reading your proof, and at the end accepting is it correct or reject, accepting the claim as being proved or not. In fact, in computer science, we often talk about efficiently verifiable proofs, or NP proofs. And those are proofs where the string that the prover sends to the verifier is short. And the verifier, in addition, doesn't have all the time in the world to read it. He has polynomial time. Now, to be more explicit, what does it mean by short? What do we mean by polynomial? What we mean is that the string that the prover sends to the verifier is of size polynomial in the length of the claim. So we think about the claim as string X, binary string. The message here is binary string W. The length of W is polynomial in the length of X. So if it takes 100 bits to describe the claim, W's length should be polynomial in 100. And the verifier's time is also polynomial in the length of X. So it could be linear, just the length of X, quadratic, length of X squared, or the length of X even to 100, as long as it's a polynomial function. Again, the verifier is an algorithm. It takes as input both X, the claim, and W, the proof string, does some processing, and at the end decides whether to accept or reject. We often say either accept or 1. And when we say reject, it's either 0 or reject. I'll use those interchangeably. What are some examples? And these are going to be important examples for the duration of the class today. One example might be of an NP proof and a claim is that the prover is trying to convince the verifier that a particular number n is a product of two large primes. This is an interesting claim because the verifier in polynomial time, we don't know of a procedure for it to be able to convince himself that n is a product of two large primes. So we need the help of a prover. Perhaps an all-powerful prover, certainly more powerful than polynomial time. Again, for this portion of the class, I don't pay any attention to how much time it took the prover to come up with a proof. All the attention that is going to be devoted to how much time it takes to verify a proof once it's sent. Later, we will dedicate our attention to the kind of claims that can be proved by a polynomial time prover who knows maybe some extra information, which enables it to convince the verifier of the correctness of the claim. So for now, let's go back to n is a product of two large prime. What's a proof? Since the prover's time might take a long time, we don't care about that. We just take attention to how much time it takes to verify. The prover just factors n. Let's say the two prime divisors are p and q, sends it over to the verifier. What does the verifier have to do? He has to multiply p times q and see that he gets n back. Multiplication is an easy operation, polynomial time. And he has to check the p and q each are both primes, and that's also an easy operation. We know how to do in polynomial time. And if that's the case, he accepts, otherwise he rejects. So after this interaction, what does the verifier really know? He knows that the claim is true, n is a product of two large primes. He knows something extra. He knows the primes themselves. It's actually more than was necessary in order to convince yourself that n is a product of two large primes. Or is it? Is there some other way to do that? We will see in a couple of slides that there is, but let's look at a few more examples. Second example. Now the prover is trying to convince the verifier that a number y is what we call a quadratic residue mod a modulus n. So the input to these two prover and verifier is a pair y and n, and the claim is y is a quadratic residue mod n. What does it mean to be a quadratic residue? It means that if you look at the equation, y is equal to x squared mod n, it's solvable. That is, there exists an x, and it's an x that's actually essentially between 1 and n, and furthermore, it's what we call relatively prime to n, so there's no divisors in common between n and x. That's a solution to this equation. So there is an x such that y is equal to x squared mod n. And what would be the proof of that? Well, maybe the verifier can do it himself. It turns out that this is a very hard problem. So it's hard, for example, to find the square root of y mod n, because if it was easy in polynomial time, the verifier wouldn't need the prover. How hard is it? It's as hard as factoring in, a well-known hard problem for classical computers. But the prover, as we said, he's all powerful, or she in this case. So she finds out an x, sends it over to the verifier squares mod n, compares to see if it's equal to y, and if so, it accepts, else it rejects. Again, it's an NP proof. There's a short string, x, that will convince the verifier to accept when the claim is correct. What happens after this interaction? The verifier is convinced that indeed there exists an x such a y is equal to x squared mod n, but he also knows x. He knows the square root of y. Last example before we start defining this more generally. Here, the claim doesn't talk about numbers. It talks about graphs. There are two graphs. Turns out, if you look more carefully in these two graphs, they are actually isomorphic to each other. In plain English, that means they are the same graph, but drawn a little differently. And formally, it means that there's a mapping from the vertices on the graph on the left to the vertices of the graph on the right, so that if you take this mapping, which we call the isomorphism, pi, from numbers 1 up to 10 on the left to numbers 1 up to 10 on the right, vertices from the left to the right, it will be the case that essentially the one on the left, if you map it to with the isomorphism to a vertex on the right, let's think of it as 1. Similarly, the 2 on the left to the 2 on the right, if there's an edge between the 1 and 2 on the left, there's also going to be an edge between the vertices that these two are mapped to on the right. And that's true for every pair of vertices. That means that these two graphs are isomorphic to each other and that pi is an isomorphism. So how hard it is to describe, how long is pi? Is it polynomial size and the size of the graph? Yeah, essentially it assigns for every vertex a name on the other graph. And that's just, essentially if there are n vertices, it's length n. And how much time does it take the verifier to check it? He has to go for every pair of vertices on the left, check if there is an edge between them on the left. There's also an edge between where they were mapped to on the right. And if there's no edge between them on the left, there should be no edge between them on the right. After the interaction, the verifier will believe that two graphs are isomorphic if he got a good isomorphism, but he also knows an isomorphism. So all of these examples are examples of NP proofs. Now, of course, we are not interested in a particular number n or particular number y or particular pairs of graphs. We're interested in the problem more generally, and we call this a language. That is all the n's which are product of two primes. That's the language of composite numbers which are product of two primes, or all the y's in n pairs such that y is the quadratic residue mod n. In other words, we're interested in languages. Formally, a language is just a set of binary strings x that satisfies some property. And an NP language is defined to be, this goes back to Cook and NP completeness, is defined to be those sets of strings, L, is an NP language, if there is some verifier, V, who runs in polynomial time, polynomial in the length of the x, such that both two conditions hold, and that is completeness and soundness. What does it mean that completeness holds? It means that when x is in the language, if you're talking about a claim, or in the example, let's say of composite numbers, when the language is a language of composite numbers which are product of two primes, and we're given such an n, then there has to be a polylog proof or witness W. The prover can send to the verifier such that the verifier examining X and W will accept. So, but completeness is not enough. We also need soundness, and that is to make absolutely sure that when X is not in the language, for this example, N is not a product of two primes, then there is no witness that will convince the verifier to accept. In other words, for all strings W that the prover may send to the verifier will reject. So we usually talk about completeness allows honest provers to convince the verifier. Soundness ensures that regardless of what a cheating prover is trying to do, he will not be able to convince you the correctness of an incorrect claim. But our question in this course is not about NP or NP completeness, but rather we're asking, is there some other way to prove these type of theorems? Can a prover, for example, convince a verifier that Y is a quadratic residue mod N without sending a square root? So this is the question that motivated Silva Micali, Charlie Rakoff, and myself to study zero-knowledge proofs in the early 80s. And this is a process that took about 3 years. The answer is yes. And the main idea, even without getting into the mathematics, is that the way that the prover will convince the verifier that the claim is true without giving away the NP proof, in the example of the Y is a quadratic residue mod N, without giving the square root, is to prove instead that I could prove it if I felt like it. So I'm not going to prove it to you, but I will prove that I could prove it. And somehow being able to prove that I could will imply that at the end, the verifier will be convinced, and yet he will not know a square root, he will not know the factors of N, he will not know an isomorphism. In fact, he will get zero knowledge in addition to the fact that his claim is true. Of course, we will need to define what it means to be zero knowledge precisely. So before we define it, I want to give you an idea of how possibly you can prove that something is a square root or the two graphs are isomorphic and so forth without actually giving the isomorphism or giving the square root. And I'm going to start just letting you know that this is no longer going to be a prover sending a string W to a verifier. We're going to need to change the proof model. We're going to need two new ingredients. One of them is going to be interaction. Rather than the verifier just passively reading the proof, he's going to have to be engaged in a non-trivial interaction with the prover. So like you see in this picture, there'll be messages going back and forth. Prover sending a message to the verifier answers back and forth, back and forth. It might be 3 steps, it might be 2 steps, it might be length of X steps, but it will be polynomial number of steps. It will be more than a single message from prover to verifier. Later on in this class, we will see that there is a way to remove much of this interaction. There will still be, in a sense, at least a single message from prover to the verifier and some preliminary stage. But for now, we have interaction. Interaction is not enough. We also have randomness. What do we mean by that? We mean that the verifier is not just going to be a deterministic algorithm evaluating what he received from the prover. He's actually going to be allowed to toss coins as a primitive operation. And his questions to the prover will depend on the result of tossing these coins. Another way to say that is that his questions are somewhat unpredictable. Because if they were all predictable, the prover could have anticipated them and just sent him the one string W in advance. But since they are unpredictable, after the prover sends a message, the verifier may ask, depending on his coin tosses, many different options. And the prover is supposed to be able to respond to all of them. What is inherent in the fact that the verifier tosses randomness is that we're also going to be willing to accept a small probability of error. What does that mean? We will get to the formal definition in a few minutes. Informally, what that will mean is that whereas in geometry class, when you gave the teacher a proof, they checked it, and it was supposed to be 100% correct. We are going to have, as a formal part of the model, allow a small probability of error, but it's going to be quantified, and you're going to have to be able to show that your error is smaller than 1 over, I don't know, Avogadro's number, or a negligible error. We'll get to that in a minute. For now, the proof model is changing. It's interactive. It's probabilistic, meaning the verifier can toss coins, that means that there's a lot of possible interactions that will come up between prover and verifier. So there are a lot of possible executions. It's still going to be the case. They both get input, which is the claim. And at the end of this question answer period, the verifier will take the history of the interaction, the coin tosses that he's made, run an algorithm, and decide whether to accept or reject. Let's look at the first example. The first example is not going to even be mathematical, but it will be something from sort of the physical world. The claim here will be that this particular page right in front of us has two colors rather than a single monochromatic color. And the scenario that I would like you to keep in mind is, let's say the prover can tell colors apart, but the verifier is colorblind. And the prover is trying to convince the verifier that this particular page has two colors. He's not going to enable him to see colors for the future. So in some sense, all he's going to convince him is that this page has two colors and nothing else. So in that sense, it will not be transferring to him anything beyond the claim. How? So here's the first step. The first step is the verifier uses his coin, he flips a coin, and with the following idea. If the coin lands on heads, he takes the page and flips it over. And if it lands on tails, he doesn't change the page at all. Let's assume that he tossed the coin, and indeed it was heads. So he flipped the pages so that what earlier was purple in the top, now it's on the bottom. And now he does this in the privacy of his own home, not showing the prover the results of his coin. But what he does is he sends the page over to the prover. The prover now looks at this page. He knew what the page looked like before, and he now sees what the page looks like now. Since the prover can distinguish colors, he can tell whether the coin landed on heads or tails, right? And indeed, that's exactly what he says. He sets out, he checks whether the page was flipped or not. He writes the value of the new coin prime, to be heads if it's flipped, tails otherwise, then he sends back coin prime. He says, listen, I think you tossed coin prime. The verifier, the rule right now is that the verifier, if indeed the coin that the verifier tossed is equal to the coin prime that the prover thinks he tossed, he says, well, it looks like the prover could tell whether the page was flipped or not. But he couldn't tell if it was only a monochromatic. So there must be two colors on this page. I accept the claim is true. Of course, if the coin that is sent over is different than what he flipped, he says, well, he couldn't even tell that it flipped it. There's certainly not two colors there. I reject. Let's try to analyze this for a minute. Clearly, if there are two colors and the prover follows this procedure, then the verifier will always accept, because the coin prime will always equal to coin. If there's a single color, the prover cannot tell whether he flipped or not. He could still try to guess, so he's a cheating prover, whether the coin landed on heads or tails. And he has a 50-50 chance of guessing correctly. So the probability that he sends the correct coin is a half at most. And if the verifier accepts in this case, the probability the verifier accepts incorrectly, because the prover was lucky, but there's a single color on this page, is 1/2. So if there are two colors, he will always accept. If there's a single color, the probability accepts is less than 1/2. There's a gap between them, but you may not like these odds. Say, what? I'm going to accept incorrect statements, claims with probability 1/2. No worries. You can repeat this process again and again. Each time the verifier tosses a new coin, decides whether to flip or not, sends the result, and so forth. And now, what is the chance that the prover, in case there is only a single color, so it's not correct claim, is able to provide the verifier each time with a correct coin he tossed? It's 1/2 the first time. It's 1/4 to be able to do this twice in a row. It's 1/8 to do this 3 times in a row, and it's 1 in 2 to the k if you repeat this k times. So the probability that the verifier will accept after k iterations of this is very, very small. So what has happened here? I was able to convince a colorblind verifier of whether a page has two colors or not, so that he always will accept when there are two pages, and he will accept that there's two pages incorrectly with extremely small probability. Let's see this again, this idea, a little bit different, of using interaction and randomness to be able to convince someone of this time a mathematical statement, without transferring sort of the obvious NP proof over. So the next example is the example that we started with, and that is the input to the proven verifier is a pair n and y, such that there exists an x such that y is equal to x squared mod n. Or is it? The prover is trying to convince the verifier that indeed this pair ny is a member of this language, the QR language, the quadratic residues language, those y's such that y equals to x squared mod n for some x. How would you convince the verifier of this case without giving him a square root? Here how it goes. The prover as a first step chooses a random value 1r between 1 and n. In fact, to be absolutely correct, this r is supposed to be between r and n and have a greatest common divisor with n, which is 1, meaning there's no common divisors between r and n. For those who don't want to really dwell into this, let's just think of it as a random number between 1 and n. And then what he sends to the verifier is r squared. Doesn't send r, he sends r squared, and let's call it s, sends up s. And he says to him, listen, if I gave you both square root of s and a square root of s times y, where y is the input, then you would be convinced that the claim is true. Because if s has a square root and s times y has a square root, then also y itself has a square root, mod n. But if I did that, that's like sending you a square root of s would be r, a square root of s times y would be r times x. Then you would know a square root of y, right? You would know x, just take r times x divided by r. And the whole point here is I don't want to give you both. So what I'm going to do is I'm only going to give you either square root of s or square root of s times y. But I want to convince you that I could have given you both square roots. And the way I convince it to you is I tell you, you get to choose. You can choose to get a square root of s or square root of s times y, your choice. And I will be able to answer either question, but I'm only going to answer one. Now, if the verifier is smart, the way to choose which he wants is going to be to flip a coin, not to decide this deterministically, but flip a coin. So then with 50-50 chance, he will, in case the prover is cheating, ask for an equation that the prover cannot solve. Why? Because if the prover is cheating, it cannot solve both finding a square root of s and a square root of s times y, because in that case, he's not cheating. So the fact that he could do both means he's not cheating. I will flip a coin as a verifier to choose a challenge. Hey, give me square root of s, or hey, give me square root of s times y. He's supposed to do that. So if my coin turned out heads or 1, the prover is supposed to give back the square root of s, which is r. And if the coin was tails, he's supposed to give the square root of s times y, which is r times the square root of y, or r times x. That's the square root of y. The verifier checks that he got the right answer. So he will accept only if indeed, when he takes what he got back and squares it, he will get back an answer for what he asked for. So if it was heads, he asked for square root of s. That in that case, it's s times y to the 0, just s. And if he asks for tails, he wants the square root of s times y. Let's analyze this. Again, if the claim is true and the prover acts according to the protocol, the verifier will always accept, because the prover can always give a square root of s and a square root of s times y. Again, the prover is all powerful. He knows the square root of y. He can, because he's all powerful. In fact, that's the only thing he needs to know. But what happens when the claim is false? Soundness is always the thing that's harder to show. If the claim is false, okay, then no matter what the prover does, the probability that he will be able to solve both equations, he can't solve both equations, he can solve one of them. So what's the probability I asked him to solve the equation that he knows how to solve? It's at most a half. Again, maybe a half is not enough for you. Repeat this 100 times. And the probability that the verifier can 100 times be so unlucky as to choose exactly the equation the prover can solve and not the other one which he cannot solve, in the case where the claim is false, is going to be vanishing with a number of trials. 1/2 if you try once, 1/4 if you try twice, 1/8 if you try third time, and 1 in 2 to the 100 if you go 100 times. And if you wanted to go k times, it's 1 in 2 to the k. So what happened here? I can convince the verifier to accept when the claim is true. It's very, very unlikely I will convince the verifier to accept when the claim is false. And I never, if you think about it, transferred the square root of x, because every time I just give him a random r, which is square root of s, or a random r times, the original x, or the square root of y. Random times the square root of y is random when you reduce it mod n. So it gives, essentially, I'm sending him random numbers which are independent of each other, even if I repeat this 100 times, because each time I start again with a verifier, with a prover choosing a new r. So what made this possible? Here's one intuition. There's lots of possible executions. So there's lots of possible interactions or proofs. And the prover essentially chooses one of those many possibilities in the first step. When he sends r squared, he's sort of choosing one of these many possibilities at random. And every proof of these many random proofs is made of exactly two parts. One part is when I ask to see the square root of s, and one part is when I ask to see the square root of s times y. Seeing either square root of s or the square root of s times y gives nothing. If the verifier could have seen both, it would imply 100% correctness. And the verifier chose at random which of these halves he wants to see, the square root of s or the square root of s times y. The ability of the prover, in principle, to provide either part is what convinces the verifier that the prover could have answered both, and therefore the claim is correct. Let's define this precisely. All right. So we have P and V, and they are an interactive proof for a language, for a set of statements. If, again, V is polynomial time, but this time probabilistic polynomial time, and there's completeness and soundness. If the claim is true, or X is a member of the language, the verifier will always accept. And soundness now has been modified. If X is not true, the claim is incorrect, or X is not a member of the language, then for all cheating prover strategy, no matter how hard they worked, the verifier will not accept except with negligible probability, like the 1 in 2 to the 100, or 1 in 2 to the k, 1 in 2 to the length of x. Let's introduce a little bit of notation. So this is a cheating prover. Every cheating prover strategy will only help the prover to convince the verifier with negligible probability. So a bit of notation. We use the following notation. We talk about the probability that PV, so open paren, PV, close paren on X, except in the case of X equal to L, X is in L, completeness is probability 1. And in the soundness case, we say that for all cheating provers P star, the probability that P star interacting with V on input X, the probability that accepts is negligible. What's a negligible function of length of X? That's a function that grows slowly than any 1 over polynomial. So that's 1 into 2 the length of X is an exponentially small function. So it's smaller than 1 over polynomial for any polynomial. Interestingly, if you step back and you think to yourself, is this reasonable to call this an interactive proof? I claim that this is ultimately what a proof is. It should convince the verifier of correct theorems, and it should not convince him of incorrect theorems. If you only are managing to convince him with a probability that is so small that in the lifetime of the universe, it's not going to happen, it's good enough for me. And that is ultimately what a proof should be. It should convince you of correct theorems and not convince you of incorrect theorems. And an event that will take time in Avogadro's number, 1 in the lifetime of the universe, of convincing of an incorrect theorem essentially never happens. All right. By the way, interestingly, is that when you have an exercise, a homework, and you're coming up with an interactive proof, sometimes it's going to take a lot of work to get you to have verify always accept correct theorems and not accept correct theorems with negligible incorrect and accept incorrect theorems with negligible probability. You don't have to work that hard. You just have to show that completeness holds with probability C, and soundness does not hold, at most holds with probability S for C and an S, which are a polynomial apart. So this will be equivalent to achieving probability 1 for C and negligible for S. This can be shown in some standard technique of using repetitions. So We define what an interactive proof for a language is. We also can talk about the class of all languages that have interactive proofs. And in the same way that we talked about NP as being all those languages for which there is an NP proof, we will talk about IP as all those languages for which there is an interactive proof. Again, the prover runtime might be very slow, but the verifier has to be polynomial time, probabilistic polynomial time. All right, we have defined what an interactive proof is. But what about zero knowledge? How do we define zero knowledge? What is even the intuition of what should be zero knowledge? So here's the intuition. I want a zero knowledge interactive proof to be the kind of proof such that whenever the statement is true, then the verifier goes through a proof, interactive proof with the prover. And at the end, he's convinced with high probability that the claim is true. But in addition to that, he has a history of interaction. He has the coins that he's tossed. Maybe you've given him so much during this interactive proof that now he can compute a lot more than he could compute before. So for the example of the n, proving that n is a product of two primes, perhaps after the interactive proof, he can factor a number or compute a square root or find an isomorphism. We will say that the interaction was zero knowledge if what the verifier can compute after the interaction is essentially the same of what he could have computed before. Namely, the interaction has not increased the computational power or allowed the verifier to compute more than he could have computed before. Furthermore, we want this to be true, not just for the honest verifier who follows the protocol, but for any verifier, even a devious, malicious adversarial verifier. This slide is an intuition. How do we mathematically capture this? Let's try. Again, we're going to do this slowly. So first of all, I want to say that this verifier has some sort of view. And I want to, so he's learned that after the interaction that the theorem is true with high probability, but he's also gotten a view. And that's the transcript, the answers and questions, plus the coins he tossed. We will define this formal variable, which is view sub v of PV on X. And that is a random variable. What I mean by that is that there's a lot of possible values that this variable can get. And this is a probability. They're distributed over the coins that V and P both tossed. Remember, let's say in the example of showing that Y is a quadratic residue, the prover tossed coins to select R. The verifier tossed coin to select whether he wants to see the square root of R squared or the square root of R squared times Y. So those are all possible executions. These are all possible assignments this variable can get. Okay, so this is the verifier's view. I will say that this view gives the verifier nothing new if the following is true. And this is called the simulation paradigm. This is the simulation paradigm has started with the concept of zero knowledge. It's used all over cryptography today. What is the simulation paradigm idea? We say that the real view, so if we look at this blurb, or this gray blurb that I call real view, which is essentially, this is a probability distribution. The points in this space are all the possible histories of interactions between prover and verifier, plus the verifier's coin. I say that this view gives the verifier nothing new if he could have actually simulated it on his own, sitting with his laptop or his computer at home, not talking to any prover. He could have come up with a simulated view. So this is again a probability distribution. He can essentially sample the simulated views himself. And what has to be true about the simulated view in terms of relation to the real view is that if there's someone else out there, like let's call him the polynomial time distinguisher, and he's pressing a button, says, give me a sample in the distribution that you have. I'm trying to determine whether I'm talking to the real view or I'm talking to the simulated view. I'm just going to keep pressing the button, getting views. And at the end, I should tell whether all the views I got were from the real view or all the views I got from the simulated view. If a distinguisher can't tell this apart, can't tell better than essentially 50-50, I say that these two views are computationally indistinguishable. A polynomial time distinguisher cannot tell them apart. let's chew into this a little bit further. What does it mean that two probability distributions are computationally distinguishable? In our case here, the two distributions are the real views and the simulated views, but it doesn't have to be applicable to this particular setting. We can talk about computational distinguishability as a notion more generally, where again, there are two distributions. In our case, there were views, but there could be just two k-bit strings. And the game is that there's a distinguisher on the other side of the wall, and he can press a button and get samples, always from either all the samples from distribution D1 or all the samples from the distribution D2. And his wish is to distinguish which is the case. We say that these two distributions are computationally indistinguishable if for whatever strategy this polynomial time distinguisher employs, so for all distinguisher algorithms, even after receiving a polynomial number of samples from the distribution sub either 1 or 2, the probability that he can guess whether this was distribution 1 or distribution 2 is less than a half plus negligible. Negligible in what? There's some sort of security parameter, which I call K here, which might be the size of the strings of the samples, the size of the sample string. So back to zero knowledge. Here's a definition. An interactive protocol, P and V, is zero knowledge for a language L if there exists a simulator, an algorithm, sim, such that for every X in L, so I'm only requiring it when the theorem is correct, only when X is in L. And why? Because you do get something, you get that X is in L. That's a detail aside. So I require that the following two probability distribution are polynomial time indistinguishable. The first is the real view that the verifier gets during an interaction. The second is an output of the simulator. The simulator here is taking X as an input, just the X. He doesn't have any square root of Y or any secrets, just the input that both P and V see. You notice here that there's another input to the simulator, which is this 1 to the power lambda. This is essentially a technicality. It's because we want to make sure that we allow the simulator to run enough time, polynomial time. And sometimes when X is really small, that doesn't give him enough time. But really, for all practical purposes, if we're thinking about large X's, forget about this one. So both of them, the simulator runs in polynomial time. To be zero knowledge means that these two distributions should be computationally indistinguishable. And that will make a protocol, PV, a zero knowledge interactive proof if it's complete, if it's sound, so it satisfies completeness and soundness, and it's zero knowledge according to this definition. Almost. Two caveats. We're going to let this sim guy, this probabilistic polynomial time, run in expected polynomial time. What that means is that the simulator might expected polynomial time essentially means that if you take the expectation of how much time the simulator runs over all possible randomness of the simulator, it's going to be a polynomial time. What essentially that means is that there might be some very, very unlucky coins for the simulator, which will take him a long time to run. But typically, he's going to run in polynomial time. This is something that you guys should know, and that is the definition of expected polynomial time. One more caveat. In this definition, I never said anything about the verifier. I just said that a particular pair of P and V is zero knowledge if the following conditions hold. But we want this to hold really the zero knowledge property for every verifier, even a cheating verifier. So the real final definition has to take into account the possibility that the verifier might be a liar and might be trying to get knowledge when he shouldn't. So he's not honest. So we finally get the definition that a protocol is zero knowledge for language L if for every V star working with P, okay, there exists a polynomial time simulator such that the view and the simulation are computationally indistinguishable. And I'm using this squiggly equality to mean computationally indistinguishable. So these might be different probability distribution, but the distinguisher cannot tell them apart. All right, so let's rest a second. So PV is zero knowledge if for every V star there was, no matter what V star does, actually we could have simulated this in our own. Why does this capture the intuition that what the ver can learn during the interaction doesn't add any computational power? Remember, our original intuition was that what you can compute before and what you can compute after is the same. The reason is because we say the following: listen, maybe there is a V star, really devious one, who can get something out of the prover. Being zero knowledge says no. If such a V star exists, then we could have computed this before, because a simulator could use that V star to come up with a simulated distribution, which is more than what the view is. But the zero knowledge requirement says that that's not possible. That for every V star, there will be a simulator that can achieve the same distribution, essentially, computationally equivalent to what can happen in the real view. And therefore, the real view did not add any computational power. All right. By the way, this is what's called a computationally indistinguishable zero knowledge. Sometimes people use the notation ZK, C for computational, but there are other flavors of zero knowledge. You can also ask for a perfect zero knowledge definition. So when the real distribution and the simulated distribution are identical, or maybe statistically close. So a perfect zero knowledge is a special case when, if you look at the view of the verifier, and then we can actually simulate it perfectly. So the simulated view and the real view are the same, and that means that they're indistinguishable for any algorithm. So this would mean that when you can prove perfect zero knowledge, it's an unconditional result. Because usually when we only prove computationally zero knowledge, we make some assumption that there are some computations which are hard. Whereas with perfect, it's just perfect zero knowledge. There's no difference between what we can learn during the view, during the real interaction, and what we can learn from a simulation. Let's work through a simulation now that we have a definition. Recall the protocol for quadratic residues. So the prover sent R squared. He asked for either seeing R or R times square root of Y. He got back an answer. He checked it. So what's the view here? The view is S. That's the first message, B, second message, and Z, third message. And what are the coin tosses are B, so it's anyway included. It's SBZ. How do we simulate that? Well, we're going to simulate this a little bit in a different order. After all, the simulator can't just choose an R and send himself a message. I mean, he could, but then if you toss a coin, so you only know how to return R. You don't know how to return R times square root of Y. So how are we going to get a simulation? The idea is as follows. And we're going to show a simulator just for an honest verifier. And in fact, the simulation is going to be a perfect zero knowledge simulation. What the simulator is going to do is, rather than really go in the order that the real interaction is that he's first going to choose the question of the verifier. And he's going to do that just the way an honest verifier would do. It picks a random bit B. Then it's going to actually pick the third answer, which is it's going to pick a random Z. Notice that Z actually is just a random number, except in this case it's R, in this case it's R times X. So the only thing that remains is to make sure that I can figure out for which S would have been Z the right answer. And note that this equation, S equal to Z squared over Y to the B mod n, satisfies exactly what S should be. Why is that? Let's look at this. Let's plug in B equal to 0, in which case S is equal to Z squared. That's exactly what it should be. In the case that B is equal to 0, Z is the square root of S. What about when B is equal to 1? Then I'm letting S to be Z squared over Y. Is that correct? Let's think about it. If you look at Z here, it's supposed to be, in the case of B equal to 1, R times X. And what's the relation of R times X to S? The relation is that if I square this, I should get S times Y. And that's exactly the case here. If I square Z, I get S times Y. So, lo and behold, I was able to come out with a triplet, which is identically distributed as what the view of the verifier, the honest verifier, is during an interaction. Obviously, this doesn't convince me of anything. It's not that I actually got an R squared and then I asked a random B and got the response. I did this in my basement in a simulation. But the view is identical. Now, what about when the verifier is not honest? So what about the case, the general case, where the verifier might not be tossing a coin and sending over? That's a little bit of a problem. What if this, adversarial verifier was the kind that when he saw some S, he did some very complicated function or computation on S, and depending on the result of his computation, would ask a particular B. Then he might have gotten something interesting depending on his computation. Well, I will show you that even if he was an adversarial, very complex computation, I could still get the same view that he did using a simulator. How is that? Again, I will pick a random B, even though he doesn't select things at random. But wait, I'm not done yet. I pick a random B, then I pick a random Z, and now is when I do something different. I say to myself, all right, I will, for a minute, suppose that indeed B would have been what he will ask me, the bad guy, the adversarial guy. And I will compute S accordingly. And now I will actually send S to this bad guy. What does it mean, send? Remember, the simulator should work correctly for every V star, for every bad guy V star. The simulator has access to V star. The intuition is that no matter how powerful the verifier is, he's polynomial time. And I have to come up with a polynomial time simulator. So a polynomial time program can have access to any other polynomial time program, including this verifier. So what I do is now is I run this verifier, the bad verifier, on the input NY and first message S and see what he asks for. If I was lucky, he's going to ask exactly the bit that I prepared for and I know how to answer. But he might not do that, in which case I can't really output S, B, Z because I just don't know the answer, the correct answers. What do I do then? I start again. I go to step one, I again pick a random bit, I again pick a random Z, I then compute S, and now I ask V star on this new N, Y, and S. Why am I hoping that this time it's going to be better? I don't know if this time it's going to be better, but I do know that whatever it is that V star is doing, this is a fixed behavior, but my B was chosen at random. What's the probability that a random bit will equal a fixed behavior? 50-50. And that means that within 2 trials, I will be lucky enough to hit on the question the V star would have asked. I suggest that you think about this more deeply and prove to yourself that the expected number of repetitions is 2 before I can output a triplet SBZ. And this is why we require the simulator to be expected polynomial time. So within expected 2 trials, I will be able to output something that is exactly the same distribution as would have happened in the real interaction. All right. I want to say that actually, if you think about this a little bit deeper, you realize that not only the prover convinced the verifier that Y has a square root, he actually proved that he knows what that square root is. Because if he can answer what the square root of S is and what the square root of S times Y is, he could actually answer the square root of Y. He never does. He always gives you only the square root of S, which is just random, or the square root of S times the square root of Y, which again, the square root of S masks the square root of Y. But if he could do both, he does actually know how to do a square root of Y. So what's hiding in here is some definition of what it means for a machine to prove to you they know something. Let's try to define that formally. We will say that a proof system is a proof of knowledge. So it's not just a proof that something is true or false, but it's a proof of knowledge for a language if the following is true. Okay, so let's think for a second. How would you define that a machine knows something? Maybe the first definition would come to mind is that it has some register and that square root is written in there, or whatever it knows is written in there. But it's not always the case. The way that we want to define that you know something, or that an algorithm knows something, is that if I could run that algorithm on multiple inputs, I could eventually compute that thing that the algorithm knows. Okay? So since the prover is an interactive algorithm, running it multiple times means that it can send me messages, I could ask it questions, it sends me messages, ask it questions, so I can run executions with the prover multiple times. If at the end I can extract W, that is the definition to mean that the prover knew W. And that's how we define proof of knowledge. We say there exists a knowledge extractor algorithm, this extractor, that can run a protocol with a prover such that in expected polynomial time, this extractor running the prover, the notation is E sub P, so he sort of has access to the prover almost as an oracle on X, will output the witness W. Now, I wanted to make one thing clear is that when I say that the extractor runs P multiple times, I can actually make it run so that he always, in every execution, he asks me the first same message. So it's like saying I can rewind him to run, to get started from the same starting point on the same randomness. This is called in the rewinding technique, which is something that happens all the time when we talk about zero knowledge. That is usually the technique to prove that something is zero knowledge, and that is a zero knowledge proof of knowledge. If we can rewind someone multiple times and eventually extract something from them, it will mean that they knew it to begin with. So here's some technicality, which I'm not going to cover, but it is the more precise definition of proof of knowledge that takes into account what was the probability that the prover managed to convince the verifier to accept. Essentially, if the probability is greater than alpha, we have always in this lecture said that in the case X is in the language, then the probability is always 1. But sometimes you will have example when the probability is not 1. It might be just greater than 2/3. Then we'll just require the extractor to run in expected time 1 over alpha, which 1 in 2/3, or 1 in polynomial, which will be polynomial still. An example of extraction. I said that the examples of quadratic residues, the prover actually knows a square root, x of y mod n. To technically show that he knows, we have to satisfy the definition. So here it goes. Here's the extractor. The extractor starts running with the prover. The first message of the prover is r squared mod n for some n. What does the extractor do? First step, it receives s and it asks the heads or 0 and gets back an r. So it stores r, and now he rewinds to the first step again. This time, though, when he gets s, he asks for tails, or b equal to 1 to 0. And he gets back rx mod n. Now he has run 2 executions. First time asking for heads, second time asking for tails. He got 2 answers, rx and r, can divide and extract the square root of y mod n. So there's definitely an extractor. So by the definition, we have just shown here in this slide that the prover knows a square root of y. And let's try it for graphs. So graph isomorphism, which we discussed before. What would be the interactive proof, the zero knowledge interactive proof for graph isomorphism? Let's go through that. It's going to be surprisingly similar to the square root example, even though we're talking about graphs. When I say similar, I don't mean that it's the same messages going back and forth, but the idea is quite similar. What is the idea? So now we're talking, there's a pair of graphs, G0, G1. The prover is this all-powerful guy. He knows, actually, in this example, an isomorphism. He wants to convince the verifier that an isomorphism exists without giving that isomorphism. How does he do it? Here is what he does. He says to the verifier, listen, I'm going to forget about the proof for a minute. Let's just say what the interaction is. He says to the verifier, I'm going to produce a random graph H, okay, like a third graph, so that I can give you an isomorphism either from G0 to H, or I can give you an isomorphism from G1 to H. These are 2 different isomorphisms. But the conclusion is, if indeed I could do both, then there's actually the direct isomorphism from G0 to G1. So you see that very quickly here on the left, on the side, if H is gamma 0 of G, an isomorphism from G0, and H is also an isomorphism from G1, a gamma 1, then you could go directly from G0 G1 by taking gamma 1 inverse of gamma 0, composition of these 2 isomorphisms. Now, the point is, again, he's not going to do both. He's only going to give him either isomorphism for G0 or G1, but he lets the verifier choose which it is. And the fact that he will be able to do both should convince the verifier that there is an isomorphism from G0 to G1 with high probability. If we break it down into the interaction, The prover sends the verifier the new graph H. The verifier tosses a coin, asks either for isomorphism from G0, isomorphism from G1, or isomorphism from G1. The prover is supposed to supply what he was asked for, and the verifier can check that he got the right thing, and only then accept. Otherwise, reject. If the statement that G0 was isomorphic to G1 is true, the prover will be able to answer, and the verifier should always accept. If the statement was false, the probability the verifier will catch a mistake, that is, we will ask to see the isomorphism from G0, and the prover won't be able to supply it because there's either just an isomorphism from G0 or from G1, or maybe from none. The probability the verifier will catch a mistake is greater or equal than 1/2. And if we do this 100 times, the probability will be catching a mistake, it will be very close to 1. 1 minus 1 into the 100, or if you repeat k times 1 minus 1 into the k. I leave it as an exercise to you that it's perfect zero knowledge. It's going to be essentially trivial if you understood the quadratic residue example to come up with the perfect zero knowledge proof here. I encourage you to do that. It's also not just a zero knowledge proof, but it's a zero knowledge proof of knowing an isomorphism. So it's a proof of knowledge. Again, to show that, you have to show an extractor. Let's show an extractor. So the extractor algorithm is allowed to run the prover. Let's do it. The prover sends you a graph H. What do? First, you set the coins to heads, and you get back an answer, which is an isomorphism from G0 to H. Second, you rewind. You start again with the same H, but this time you ask for tails, and he will give you an isomorphism from G1 to H. And now you can combine the isomorphism from G0 to H with the isomorphism from G1 to H to get a direct isomorphism from G0 to G1. The end. We are able to extract the isomorphism, and therefore we know that this was a proof of a knowledge of an isomorphism. Great. Why did I talk about proofs of knowledge? Because it gives us immediate corollary and application, and that is the first application that Fiat Shamir proposed a few months after we wrote the paper about zero knowledge for identity theft. And they're saying, look, Alice wants to prove over the internet that she is Alice to Bob. Bob could be Amazon, say. Over the net means something could be listening. But even more interestingly, suppose nobody was listening, but Amazon had to store all those passwords in order to recognize Alice when she comes in. What if somebody breaks into Amazon? You don't want those app passwords in the clear. You don't even want those passwords encrypted, because maybe the encryption that Amazon does, one can sort of do a birthday attack, or there's a lot of other attacks that you can on a password file. Is it possible that Alice can convince Bob she's Alice in a different mechanism without Bob actually being able to turn around and convince someone else that they are Alice without a break-in attack? And the answer is yes. Zero knowledge proofs gives you the mechanism. Now we think about the password of Alice as knowing the proof of a hard theorem. So you can think of Alice as someone who takes an X, squares it, calls that Y, and says, hey, I know a square root of Y mod N. That's a hard theorem, but whoever knows it, that's Alice. How does she convince Amazon, a mainframe, an ATM, someone who just wants to know that Alice is the right person, but shouldn't really know Alice's proof for the hard theorem? A zero knowledge proof. So they would go through a few steps of interaction, at the end of which it says, she knows a square root. She just given me a zero knowledge proof of knowledge, and that identifies her. So somehow it's possible to verify that Alice knows the proof without knowing the proof yourself. It's not the only example of an application, but in order to get many more applications, including applications in the realm of blockchains, we need to do one more thing, and that is a big thing. We've seen the example that two graphs are isomorphic. We've seen the example that Y is a quadratic residue mod N. But there are lots of other languages. So let's ask a really big question. Do all NP languages have a zero-knowledge interactive proof? Whoa, that would be amazing. But how are we going to do that? Are we going to go for every single NP language and show that they have a zero-knowledge proof? No. So in 1986, Goldwasser, Micali, and Vigderson showed that if one-way functions exist, then every language in NP has a zero-knowledge interactive proof. Let's dwell on this statement. There is a condition here. When we showed that graph isomorphism has perfect zero knowledge or quadratic residues of perfect zero knowledge, there was no condition. Here, the condition is that one-way functions exist. This is essentially the simplest condition or the simplest assumption that we use in cryptography. It will be covered in the supplementary material, but for now, let's just assume that factoring is hard, or discrete logs are hard, or bilinear maps are hard. That will be an instantiation of one-way function. And then they showed that for every language in NP, there is a zero-knowledge interactive proof, a computational zero-knowledge interactive proof. It won't be a perfect one, but it will be using the general definition of computational. There were two main ideas in the proof. The first key idea is to show that an example of an NP complete problem that has a zero-knowledge interactive proof. That will be sufficient to establish that every language in NP has a computational zero-knowledge interactive proof. Why is that? Due to NP completeness reducibility, if a language is an NP complete, then every string X can be reduced. Let's say if we're talking about the three coloring NP complete language, every instance X will be reduced to a graph, G sub X, such that if X is in the language, then the graph is three colorable. And if X is not in the language, then the graph is not three colorable. That means that if I had a way now to have a zero-knowledge interactive proof of whether the graph G sub X is three colorable, it will also imply that I have a zero-knowledge interactive proof of X being in the language for every language which is in NP. So what they showed in their paper is a zero-knowledge interactive proof for a particular NP complete problem, the three coloring problem. And I'll show you in a minute how to do that. But they needed one ingredient, and that is where the one-way functions come in. They needed essentially to use the one-way function to get a primitive, a cryptographic primitive called a commitment scheme. And that is the second idea. So one-way functions imply actually a bit commitment scheme. What's a commitment scheme? Essentially, a commitment scheme or commitment protocol is a pair of protocols, a commit protocol and decommit. A commit protocol takes as input an M. Usually I want to think of M as a bit. It's either 0 or 1. And essentially, metaphorically, puts M in an envelope, seals it, so it's an opaque envelope. There's a sender and a receiver. The sender commits, the receiver gets the envelope, can't tell whether there's a 0 or 1 being committed to. Then there's a decommit protocol where the receiver can actually open the envelope and show that the sender opens the envelope and shows the receiver that what was in there was either 0 or 1. The properties of these two protocols is that they satisfy hiding and binding. Hiding means that while it's committed, you can't tell whether it's 0 or 1 better than 50-50. And binding means that when you open the envelope, you can't have committed to 0 and open to 1. Whatever it is you committed to, you are actually bound to it to reveal it. We can go in a little bit more detail here, talking about exact definition for hiding, and that is that really the view of the receiver when you commit to a bit B or a bit B prime is this computationally indistinguishable. And binding is that you are not able to decommit to two different values, B and B prime. What is an example of how to get a bit commitment scheme? The simplest example is using encryption. You can think of commit as the sender essentially encrypting the bit. If you want to commit to a bit B, you encrypt a bit B. And you can think of decommitting then is giving the receiver either the decryption key or the randomness you used in order to encrypt the bit B. It's very important there will be a randomized scheme for hiding to hold, because I really want to be able to hide very strongly. So you cannot tell apart whether what you've committed to is 0 or 1. And for that, you need a probabilistic encryption scheme. So let's go to the main act, and that is, how do you show that a graph is three-colorable without giving the coloring? In fact, in computational zero knowledge, having access to this commitment and decommitment primitives. Here's the idea. So the prover, again, he knows all. He doesn't only have the graph, like the verifier and the prover both have the graph, he actually has a coloring. So let's say he has a coloring of the vertices to red, blue, and green. Or we can call these colors the zero color, the one color, and the two color. The first step, what the prover does, it's very different, by the way, than the protocols we've seen before. What he does now, he picks a random permutation, which is a step that's unclear why, but we'll explain it in a minute. Rather than using the original coloring, he takes actually a permutation of those three colors. So there's 6 permutations of that, like red could be now blue, blue could be green, green could be red, or any of the other 5 possibilities. So you pick a random permutation of those colors, and now you go to all the vertices of the graph and you recolor them with, take the old coloring and recolor it according to the random permutation that you chose. Now the graph is 3-colored. If the prover is claiming a correct proof, there is a 3-coloring, and you just colored it again with a sort of a permutation of this 3-coloring. And now what the prover does is he commits to each of these colors by running a commit protocol. In other words, he sends to the verifier a commitment to, for every vertex, it will be the commitment to red, to blue, or to green. A commitment means it's hidden. The verifier gets this, but he can't tell what the heck are the colors. What the verifier now does is the following. He thinks to himself, well, either this is a proper coloring or it isn't. If it isn't, it means that there's at least one edge in this graph that if you look at the 2 endpoints, they're going to have the same color, or maybe some other color altogether. But to be a proper 3-coloring means that you only use red, green, and blue, and for every edge, the 2 endpoints are different colors. So what the verifier says, I have no idea which one of these edges is wrong. Maybe they're all correct, but I am trying to catch the mistake. So what I'm going to do is I'm going to select a random edge among all the edges, and I'll send it to the prover. And I'll say, you see this edge? I want you to decommit the colors at the endpoints of the 2 endpoints of this edge. And that's exactly what the prover is supposed to do. He's supposed to sort of open the envelopes that have to do with vertex A and vertex B. And now there's the edge AB has been decommitted in some sense, the colors of the endpoints. And the verifier, of course, if the colors are not 2 different colors, he rejects immediately. Otherwise, he goes back to step 1 and repeats it again. And after k iterations, maybe k is 100, if he never rejected, he never found an edge that has anything but 2 different colors, he will accept. Let's analyze this. I will analyze it in the next slide, but I want you to think for a second about the zero knowledge aspect. What has the verifier found? One iteration, he found the colors of a single edge. But what about the second iteration? As someone asked me in class, maybe he can build up after 100 iteration or more, a partial coloring, or maybe the entire coloring. No. And that is why? Because in step 1, remember, I picked a random permutation of the base coloring. Why did I do that? I did it so that even though I'm repeating this again and again and again, each time selecting maybe different edges, the verifier is selecting different edges, the colors mean different things. Whereas before blue meant blue, now when I put a random permutation of the colors, blue might mean something completely different. In fact, you can prove that these colorings are uncorrelated between repetitions. Okay, so we need to prove that this is zero knowledge. We need to prove completeness, soundness, and zero knowledgeness. Completeness, what does that mean? If the graph is 3-colorable, that the prover, an honest prover, can always convince the verifier to accept. Yes, because he can always color it properly. And no matter what edge is being requested, he can always give the proper coloring. What about soundness? If the graph is not 3-colorable, now think about it. No matter what the prover P star does, there is one edge there that's not properly colored. What's the probability that when the verifier chose that random edge, he will actually hit on the edge that is not properly colored? Pretty small. Maybe everything is well colored except for one edge. What's the chance you get that edge? Well, the chance is 1 in the number of edges. So the probability that after one trial, one iteration of this, the probability the verifier will accept when the graph is not 3-colorable is pretty good. It's 1 minus 1 in E. That's not good enough. We want the probability that it accepts to be small in this case. So repeat again, but how many repetitions? Twice won't be enough. Because 1 minus 1 in E times 1 minus 1 in E, it's a little smaller than 1 minus 1 in E, but not much. But if I repeat this, the number of edges, number of times, then it will disappear exponentially. We will have 1 in natural log, so 1 in little e, to the number of edges. And that is an exponentially small probability. And we get this gap between completeness and soundness. You will always accept, the verifier will always accept when the graph is 3-colorable, and he will accept with exponentially small probability when the graph is not 3-colorable. Now, zero knowledge, as I said, it's easy to see informally. It's messy to prove it formally. So how do we see it? At least I'll give you some inkling of the proof, and let's do it for the honest verifier. So the honest verifier computational zero knowledge works like this. This is the simulation. The simulation, again, works in a different order. Rather than first taking a coloring and committing, how can he do that? The simulator doesn't know coloring. There's no way he can do that. Can't even get off the ground. So what the simulator does is it chooses at random in advance the challenge of the honest verifier, which is just a random edge. Then it chooses a bunch of colors, which really don't matter. He can color the whole graph in the same color, except for that edge that in the lucky execution, the verifier will ask him. That's the AB edge. And it colors it in 2 different colors, 2 different random colors. And what is a simulated view it outputs? It commits to the transcript, which is a bunch of commitments, okay? The commitments are not supposed to give anything to a computationally bounded distinguisher because they're just commitments. Or if you think about how we implement the commitments, a bunch of encryptions. So you can't see anything. Then you give an edge. The honest verifier put the random edge. And then you have a decommitment transcript to those colors. And the decommitment transcript will give 2 different colors to A and B because my commitment made it so that I essentially, the only colors that were different were on that edge A and B. This is exactly a kosher transcript, but is it? Not really. If you think about what has been committed to, it's not illegal coloring. So this transcript is very different than what happens in the real interaction, but it is computationally indistinguishable. And that depends on the hiding property of the commitment protocol. So what does the simulation look like? The simulation, which doesn't talk about honest verifiers, but for every verifier, that's harder. It's here on the slide. I will leave it for the TA to discuss in the supplementary lecture. The upshot of this, now that we know that all of NP can be done has an interactive zero knowledge proof, it means that we have many, many, many examples which are interesting for us, as many as there are NP languages. Obviously, we can use this protocol also for the statements we already know perfect zero knowledge for, but we can get a stronger guarantee with perfect zero knowledge. But the more interesting cases is when we don't know a perfect zero knowledge protocol and we have to go through this 3-coloring protocol. So an example, any satisfiable Boolean formula to prove that it has a satisfying assignment can be done in zero knowledge without actually giving the assignment. Given an encrypted input E of X and a program, prog, I can prove to you in zero knowledge that if you ran this program on X that you only see the encryption of, you will get Y. In fact, I can give you an encrypted input, an encrypted program, and prove to you that if you ran that program on the input, you would get back Y. And that is without revealing the input or the program. Why is that important? Here are applications. First major application that they already noticed in the original paper is a protocol design application. Essentially, this is a tool to enforce owners' behavior in cryptographic protocols without revealing any knowledge or information. The idea is the following. Suppose you take a protocol and you've proved that if all players follow honestly the protocol steps, it's a safe, secure protocol. Now you run it in the wild. The players may not follow the protocol, but you want to make sure that you can still use your security protocol proof. What do? You tell the players, okay, I want you, along with every message you send, to give me a zero-knowledge proof, a zero-knowledge interactive proof, possibly, that the next message that you're sending, that is the message you're sending, is what you should have sent if you were honest. In other words, it's what the protocol rules would tell you to send on the history of communication so far and your internal randomness are, and maybe some other internal inputs. How do you prove that in zero knowledge? Essentially, you commit to the internal randomness, you commit your internal secrets once and for all when the protocol starts, and then every time you send a message, you attach a zero knowledge proof that on these committed randomness, on these committed private inputs, this is the right message to be sent. Why can this be done? Because that is an NP statement. So if you think about the language, there exists some randomness such that the next message is what is equal to the protocol on the history of communication in R. And in fact, R has been committed to, that's an NP statement. Again, that's a mouthful. I advise you to mill over this, but it is an amazingly powerful tool. Zero knowledge has been used for many things. You know, in the 80s, it was mostly the two applications I already mentioned, which is identity, preventing identity theft, and a tool for protocol transformation from honest to dishonest players. But since then, it's been used in the context of computation delegation. If you want to delegate computation to the cloud, but only give the cloud encrypted data. It's even been discussed as a tool for nuclear disarmament. That's a very interesting application of the concept of zero knowledge, that actually nuclear physicists have been, at least about 10 years ago, there was a lot of work in this field. People have suggested to use it in the context of forensics to prove, for example, that your DNA is not the DNA that's on the crime scene without revealing your DNA. But in the context of this class and the huge boom that has happened to zero knowledge, it's mostly started with a paper by Ben Sasson, Chiesa, and others on how to do Bitcoin in a private and anonymous manner. So adding ZK proofs in the context of cryptocurrency. More recently, there's some work by Bamberger and Rebecca Wexler and Ron Canetti and Evan Zimmerman and myself that shows that zero knowledge might be a very important tool in the context of the legal domain, where there's many verification dilemmas in the law that necessitate right now revealing a lot of information that you might not want to reveal, and zero knowledge can be used instead. The last thing I want to say is that zero knowledge has been not only useful for cryptographic type applications, but it's actually been sort of revolutionary in the context of complexity theory. And in fact, it's not so much zero knowledge, but really the concept of interactive proofs. So I'm going to spend the last 5 minutes talking about that before we end the class today. So when we talk about what's efficiently solvable, what's an efficient algorithm, we usually talk about P, polynomial time, things that run in polynomial time, or things that run in polynomial time plus coins. When we talk about what's efficiently verifiable, we used to talk about NP. But in this lecture, I suggested a new form of proof, an interactive proof, where essentially you take NP and you add interaction and randomness on the part of the verifier. Notice that our verifier was pretty simple in the perfect zero knowledge examples. He was just choosing a coin and sending it over. And also in the NP 3 coloring zero knowledge proof, the verifier chose a random edge. Is there something more sophisticated the verifier can do? Here is an example. I'll show an example of an interactive proof for a statement which is not an NP statement, where the verifier is doing something a little bit more than just tossing coins. Okay, and this will answer 2 questions at the same time. One is Can you interactively convince a verifier in polynomial time of statements that we don't know how to convince using a classical old NP proof, just sending a witness? And the answer is going to be yes. And second of all, is there something else that verifier can do except for tossing coins? And the answer for the next minute will be maybe. Let me show you an example. Suppose I wanted to prove as a prover to the verifier that actually these two graphs, which are different from the other graphs, are not isomorphic to each other. Is this any different than the previous picture? Yes, I've added an edge here on the left graph, G0 between 7 and 4, and on the right between 4 and 10. What adding this edge has done is we've maintained the number of vertices and edges, but it's no longer true that these two graphs are isomorphic to each other. How do I prove that to the verifier? Think about it for a minute. I can't give an isomorphism because they're not isomorphic. I guess one thing to do is to go through all possible isomorphisms and to show one by one that neither one of them works, or none of them work. But there are a lot of isomorphism. So that is going to take a long time. There's an exponential number of isomorphisms and factorial. But I want to convince an efficient verifier. So even though I don't have a short proof to send over, like an NP type proof, I will show you how to convince an efficient verifier interactively that two graphs are not isomorphic to each other, so that completeness and soundness hold, and also zero knowledge, actually. Here's the idea. Let me fill everything in and then go through it. Step one, the verifier flips. So the input is two graphs, G0, G1, and the claim is that they are not isomorphic to each other. There is no isomorphism that maps the vertices of G0 to G1. Step one, the verifier flips a coin, 0 or 1. And he does that in order to select either G0 or G1. And he also picks a random isomorphism, okay, a permutation of the n vertices. And then he applies this isomorphism to either to G sub the coin. So let's say if the coin was 0, he applies it to G0. If the coin was 1, he applies it to G1. That gives him a graph H, which he sends over to the prover. Now this graph is an isomorphic copy of G sub C. Notice that if the two graphs were isomorphic, so it was an incorrect claim, this graph actually H is isomorphic to G0, but is also isomorphic to G1. How does the prover know which is the case? Well, if indeed the two graphs are not isomorphic to each other, and he's an all-powerful person, remember that's how we were thinking about the prover, he just examines whether H is isomorphic to 0 or G1, and he tells back to the verifier which is the case. If the verifier knows whether he took an isomorphism of G0 or G1, if B is equal to his coin, he's happy. If B is not equal to his coin, he immediately rejects. He says, hey, this guy couldn't tell whether it was an isomorphism of G0 or G1. He must be a liar. These two guys must be isomorphic to each other. I reject. However, as usual, he could have been lucky. He could have guessed the right coin, even though H is isomorphic to only to both G0 or G1. He could have guessed that the coin flip was 0, say, and convinced the verifier, or at least not convinced the verifier, or left the verifier ambivalent. So the probability that he succeeds to do that is going to be at most a half. We do this as usual, k times. The probability that you will always get the result of the coin of the verifier is a half the first time, a quarter twice in a row, and 8 3 times in a row, and 1 in 2 to the k times in a row. So when the two graphs are isomorphic, you'll catch him. When they are not isomorphic, he can always convince you. So completeness and soundness hold. But does zero knowledge hold for this protocol? Let's think about it. Even intuitively, before we try to do a simulation and fail, it doesn't. Why is that? Because the honest verifier, yes, the honest verifier, no problem. But if the verifier was not honest, maybe he didn't just take a random H, apply it to the G sub C and send over H. If he was honest and he did that, all he finds back is the result of his coin, which he knows if it's what the coin was. But maybe he's a cheater. If he's a cheater, he might be sending H's here that he just wants to find. He's finding out whether this graph H is isomorphic to G0 or G1, right? So when a dishonest verifier is working with an honest prover who's giving him, essentially is telling him whether this new H is isomorphic to G0 or G1, this is knowledge that I don't know how to simulate. And in fact, this is an example of a protocol, which is an interactive proof. It's a non-trivial interactive proof. Like it convinces the verifier. We don't know how to convince the verifier of non-isomorphism with an NP proof, but it's not zero knowledge. We will need to modify it to be zero knowledge. How do we modify it to be zero knowledge? The verifier essentially, before the prover answers, will have to prove to the prover. So now we sort of a switcheroo. He's going to send him H, and then he will prove to him that actually he knows that he really did these steps. He really applied this isomorphism to G sub C. And it's beyond the scope here, but there is a way for the verifier to do that. What's interesting about this protocol is that it was very important for this protocol to work that the verifier here did more than just flip a coin. He actually he flipped a coin, he picked this random gamma, and he didn't reveal to the prover the result of his coin tosses. It's actually kind of interesting that the prover is the one who gives back B, but the verifier flips some coins in secrecy and then sends over H. If you think about it, this actually is very similar to the example of the colorblind in the beginning of the lecture. The issue is that it brings up a general question, and that is a question that came up around the same time that the zero knowledge paper came. There was a proposal of something called an Arthur Merlin game by Babai and Moran, which is an interaction between a prover and a verifier. He called them Merlin and Arthur. The difference was that Arthur wasn't a probabilistic polynomial time algorithm that tossed coin and did computation. He was just a coin tosser. He threw coins, got back, threw coins, got back. This was the case actually in the perfect zero knowledge proofs that we've seen, and also in the three coloring case. But it was not the case for this last example that I showed you. And the question was asked, is it really the case that maybe you can prove more theorems like non-isomorphism if you let the verifier Arthur hide his coins? Or in other words, is IP, interactive proofs, more powerful than Arthur Merlin, what they called Arthur Merlin games? Is the privacy coin necessary in order for the prover to convince statements which are not in NP? The answer was no. Actually, you can take any interactive proof like the one we just showed for graph non-isomorphism and turn it automatically to a system where the Arthur or the verifier only tosses coins. Turns out that this transformation is such that it makes it so that even if Merlin was efficient to begin with, he will become inefficient. But again, this is for a complexity course. There are lots of other questions people asked. And that was, how exactly powerful are interactive proofs? Okay, so you can do graph non-isomorphism. Can you do more than that? The answer is that you can do actually a lot more than that. But before I show you that, I want to say that protocols where Arthur or the verifier is only a coin tosser are very interesting protocols in practice, because it has been suggested by Fiat and Shamir in a paper on suggesting something called the Fiat-Shamir paradigm, or at least since then we call it the Fiat-Shamir paradigm, is that when you have a protocol where the prover is sending messages, but the verifier always doing is sending coins, you could possibly get rid of interaction. Now, getting rid of interaction is a big one. If we can transform all this to like the prover just sending a string, that would be amazing. How could you get rid of interaction? The suggestion of Fiat-Shamir was this. They said, let's assume for a minute that we had access to some H, big H, which we think of as a cryptographic hash function. Again, this is for the supplementary material. For the purposes of my lecture, let's just think of H as a random oracle. What does that mean? H, basically, I can apply it to a string and get random coins, something that really looks unpredictable. then if such an H existed, what the prover can do is say, well, there's some interactive proof, and let's say we prove completeness and soundness about it. What I can do instead of really interacting, sending A1, getting back coins, sending A2, and so forth, what I'll do is I will send you a string, which is my first message A1, and instead of waiting for your message with coins, I will by myself apply big H, this hash function, to my own message. And since I'm told this H really just takes the message and outputs something that looks random, I will now view this as your question, your coin question, and answer that. And this transcript, rather than A1 coins A2, it's A1, the result of applying the hash function to A1, A2, should be just as good, and the verifier can run his decision procedure on this history rather than on a true interaction, and then decide either to accept or reject. It should be satisfy completeness and soundness in the same way as a real interaction did. A lot of people use this feature mirror in practice, this paradigm. It's a heuristic. Why do I say it's a heuristic? Because we don't really have such cryptographic hash functions that take a string and give me something at random. That is an idealization. It's called a random oracle model, but it is used in practice all the time. What you can say that if H is behaving like a random oracle, then completeness and soundness do hold. All right. Warning, this does not mean that all interactive zero-knowledge proofs can be made non-interactive. Okay, even though IP is equal to AM, it's not true that all interactive proof protocols where the verifier hides his coin can be turned into zero-knowledge interactive proofs where Arthur doesn't hide his coins. But it can benefit many protocols. And just one other thing is, notice that what I did here in this slide, I looked at a case where the first message is from Merlin, the second message is coins. But in some of the protocols we've seen, the first message is actually from the verifier. Then how do you make that non-interactive? Well, usually what happens is, and that is going to be used in the course extensively, is that we will post the first message coins as sort of a publicly chosen randomness for all to see, and then apply the feature mirror heuristics to get non-interactive proofs. The notion of interactive proofs has been really a catalyst for complexity theory, because it was the first time that we really decoupled correctness from the knowledge of the proof. And it enabled people to ask a lot of new questions about the nature of a proof. These questions have been asked, and some of them have been answered for the last 30 plus years. And it's leading up to actually current research on, provably outsourcing computation and some research in quantum computation. Some highlights. Well, classically, before interactive proofs, the notion of efficient verification was NP. That is, that there exists a solution, so I just send you the solution and you, as a verifier, check it. We didn't know how to verify whether co-NP statements were correct, like the two graphs are not isomorphic to each other. Co-NP are the complement to NP languages. To count how many solutions are there to a statement. So, for example, if you have a Boolean formula, how many, and you want to find out, does there exist a solution? That's an NP statement. There exists no solutions, that's a co-NP statement. There are exactly 37 correct solution, that's what's called a Sharpie statement. We don't know how to convince a verifier of that efficiently using an NP proof. Or even a more complex statement where you have an alternation of quantifiers, like for all X, there exists a Y, for all X2, there exists a Z, and so forth. We have no idea how to convince a polynomial time prover of such statements. However, if we use interactive proofs, it turns out we can. So just by adding interaction and randomness, it has been shown in an amazing paper by Fortnow, Karloff, by Elund and Nissan, and then by Shamir, that you can convince a polynomial time probabilistic verifier with a very powerful prover, but polynomial number of messages, that even statements in P space can be proved using an interactive proof. Not only that, but people have thought, they said, well, interaction helps, coins help. Maybe there's other ways to define probabilistic proof system. And in fact, in a joint paper with Benor, Killian, and Vigderson, we came with one such statement. And we said, one prover, we were able to do p-space. What if we add another one? So to begin with, you say, why would 2 be better than 1? I mean, they're all powerful. What does that add? The idea was that we will let these 2 provers, this one will interact with the verifier, and this one will interact with the verifier, but they won't see each other's messages. And we likened it as if there was an interrogation of these 2 provers, like interrogating someone in the crime. What's the crime? There's a claim. If the claim is true, there's no crime. If the claim is false, and he's trying to convince you that it's true, there's a crime. There's a bug in the proof, you're trying to find it. And we were able to show, indeed, that if you use this kind of proof system, you can get unconditional zero knowledge, so perfect zero knowledge for all of NP. But more interestingly, it turned out that in some incredible sequence of events, it was shown that 2 provers can actually convince you of even more statements than p-space. The kind of intuition is the power of 2 provers, which are in different sort of interrogation rooms, is that you can catch inconsistency. So they have to be consistent for you to accept their proof of a claim. And catching inconsistency is an incredibly powerful device. And in fact, it's been shown you can even convince a polynomial time verifier of non-deterministic exponential time statements. This has led to sort of, incredible theorem called the PCP theorem, saying that even if you stuck back to NP statements, back to the usual good old NP statements where you have short witnesses for, there is a way to verify them being correct with very high probability by only reading a constant number of bits of the proof. So this is like going somewhere completely different, but it is a result of interactive proofs because we are allowing the verifier to make an error. We're allowing him to toss coins. And what has been shown is that by coming up with a sort of very different mechanism for writing proofs down, you could write them in such a way that you could only need to read a few random locations in order to find an error. It's another way to think of a 2-prover proof system. As I said, it had an impact on quantum computing, and one of the beautiful results there is the result of some people from Berkeley, Umesh Vazirani and others, and that is, how do we know that a quantum computer is actually using quantum power if we only have classical powers? And what they showed is a way to take essentially a claimed efficient quantum computation, 2 copies of it, likening the 2 provers, make them sort of sit in separate rooms, but be entangled, and show how you could convince a classical verifier of the correctness of the computation by choosing coins and by using entanglement. And then this leads up to something very, very recent, showing that actually, if you have 2 provers, so not necessarily efficient quantum computers, but 2 quantum computers who might be taking a long time, they can convince a classical verifier of languages which are they recursively enumerable languages. That's kind of an amazing statement. It's an amazing theorem. There's a lot of buzz around it today. All right, thank you.